Welcome! Today we're going to jump right into the stack data structure. It's honestly one of the simplest but most powerful tools in all of computer science. It's a fundamental concept, so let's get straight to it.
All right, so here's our game plan. First, we'll cover the core idea of what a stack even is. Then, we'll look at where you actually see them in the real world. After that, we'll dive into how they work. And finally, we'll check out the two main ways to build one, with an array and with a linked list.
So what exactly is a stack? Before we even think about code or anything complicated, let's start with a really simple idea you already get from your everyday life. Okay, the absolute best way to think about a stack is to just picture a stack of plates, right? When you add a new plate, you put it on top. And when you need to grab a plate, which one do you take? The one right on top, of course. That is the core principle. Last in, first out. Or as you'll always hear it, LIFO. And this brings us to the golden rule of stacks. Whatever you just put in is the only thing you can take out next. That's it. This strict order is what makes them so reliable and predictable. We call adding an element pushing it onto the stack, and when we remove it, we call that popping it off. So why do we care so much about this simple last in, first out idea? Well, it turns out this abstract concept is secretly running the show behind a ton of features you probably use every single day. Seriously, stacks are everywhere. Ever use the undo button? Every time you type something or make a change, that action gets pushed onto a stack. When you hit undo, the program just pops the last action off. What about the back button in your browser? Same exact thing. Each page you visit gets pushed onto a stack, and clicking back just pops you to the previous one. It's a really elegant solution for anything that needs to happen in reverse order. Okay, so now that we know the what and the why, let's pop the hood and see how they actually work by looking at the specific actions or operations we can perform. These 5 operations are pretty much the entire toolkit for any stack. Push is how you add a new item to the top. Pop is how you remove that top item. Then there's top, which is sometimes called peek. It lets you look at the top item without actually taking it off. And finally, isEmpty and size are just little helpers that tell you about the stack's current state. That's the whole shebang. Now, this is a really important point. There are 2 main flavors of stacks. First, you can build one using something with a fixed size, like an array. This is super fast, but it has a hard limit. Try to cram one more item in there when it's full. Boom, you get what's called an overflow error. The other way is to use a dynamic structure, like a linked list, which can just grow and shrink whenever you need it to, completely avoiding that overflow problem. So let's dig into that first method. Building a stack with an array is probably the most straightforward way to do it, and it's a fantastic way to really understand the logic underneath. To build our array-based stack, we really only need 3 things. The array itself, of course, a variable to hold its maximum size, or capacity, and an index we'll call top. Now here's a little trick that makes life easier. We start top at -1. Why? Because it's a super clear signal that right from the beginning, the stack is totally empty. So how does push actually work with an array? First, you got to check if there's even any room left. If our top index has reached the very last slot in the array, it's full. That's our overflow condition. But if there is room, it's easy. We just move top up by 1, and then we drop our new element into that new top position. Simple as that. And popping is just the reverse. First, we check if the stack is empty. If top is still at -1, there's nothing to pop. If it's not empty, we grab the value at the current top position. Then we just decrease top by 1. And here's the cool part. You don't even have to erase the old data, but just moving that top pointer back, you're essentially saying this spot is now free game for the next push. So that's the fixed-sized array, but what happens if you have no idea how big your stack needs to get? Well, this is where the dynamic approach using a linked list really shines, because it solves that overflow problem completely. With a linked list, our stack is made up of individual nodes. You can think of each node as its own little package. Inside, you've got 2 things, your actual data and a pointer, which is basically an arrow that points to the next package in the chain. All we need to manage this whole chain is just one pointer, which we call top, that always points to the newest node at the very front of the list. Pushing with a linked list is a really clean 3-step dance. 1, you create a brand new node for your data. 2, you tell that new node's arrow to point to whatever was the old top. And 3, you update the top pointer to point to your new node. Just like that, it's the new front of the line. You can do this over and over as long as you have memory, no overflow. Popping is just as slick. First, you check if the stack is empty. If top is null, it means the pointer isn't pointing to anything, so there's nothing to pop. Otherwise, you just move the top pointer one step down the chain to whatever the next node was. The old top node is now disconnected from the list, and we can safely delete it to free up that memory. All right, so let's put these two side by side. What's the final verdict? The array-based stack is simple and uses memory very efficiently, but its size is fixed, so you always have that risk of overflow. The linked list stack is dynamic, it's flexible, but every single node needs a little extra memory for that pointer, and that can add up. So the choice really just depends on whether you know your maximum size ahead of time or not. And here's what that looks like in some simplified code. You can see that push function checking for overflow and pop making sure it's not empty before it moves that top index. It's exactly what we just walked through, just written out. And here's the linked list version. You can see how the push operation is all about creating a new node and just shuffling around those pointers. And pop is just reassigning the top pointer. It's all about managing that chain of nodes. Okay, so if you remember just 3 things from all this, make it these. Number 1, stacks are all about LIFO, last in, first out. Number 2, their entire world revolves around a few core operations, push, pop, and top. And number 3, you can build them with either a fixed size array or a flexible linked list, and each has its own pros and cons. And that brings us to one last little thought. We've totally mastered last in, first out. But what if your problem needed the exact opposite? What if you needed the first thing you put in to be the first one you could take out? Kind of like a line in a grocery store? Well, that, my friends, is a whole different data structure and a story for another time.
I really hope this gives you a solid handle on the stack data structure. Thanks so much for joining me on this explainer.